sounds very faster than before. Okay, transition states. This is in the kinetics. We deal with kinetics. Transition state is a state where the between the reactant and the product, and especially the elementary steps, where the bond is about to form and the old bond is about to break. That's the moment we call it transition state. So, for example, this is a methyl bromide react with a chloride reaction. This reaction, next chapter will be focused on, is a nucleophilic substitution. So, which means the chlorine will substitute the bromine in the molecule. And the transition state is where the chloride incoming is about to form a new bond, and the carbon bromide bond, the old bond, is about to break. And the moment they are just about forming bond, breaking bond, that's a transition state. This transition state is one of the highest energy spot. It's one of the energy maxima, high energy spot, because molecule at this stage is not octet. It has extra electrons. And the transition state is a very brief moment, will not be stable, is not observable. And so the analogy will be the high jumper right over the bar to reach the highest energy position. It is the transition state. The reaction intermediate. The reaction intermediate is we really should pay more attention, because in the organic chemical reaction, students are supposed to be able to write down the steps, the mechanisms of a certain organic chemical reaction. And then for those steps, each step produces a reaction intermediate. So the reaction intermediate is more important. And the reaction intermediate is something we form in the middle of the reaction, high energy, not quite stable, but can exist. And in the energy diagram shows, for example, this is a two-step reaction. First step, you go through a transition state, and it formed the intermediates. Is something formed in between. Is in the valley. Is one of the trough in the energy diagram. It's fairly stable, but not very stable. It is followed by the next step reaction. Next step, you have fairly small activation in barrier and becomes a more stable product. So this is high energy state. It is a reaction intermediate. Reaction intermediate in chemical reaction, oftentimes we can observe using instrument, sometimes by the color, because some intermediate, such as carbocations or anions, might have a special color or absorption at certain wavelengths. We can observe them. And that's the difference between the intermediates and the transition state. The transition state sometimes we discuss, but that's not something it really forms in the middle of the reaction. It is a stage that is going through. And so this is a 1, 2, 3, a three-step reaction mechanism. Three-step reaction mechanism. And you can see there are 3 transition states because there are 3 steps. And there are 2 reaction intermediates. This is the first step reaction intermediate. And this step intermediate is not stable. It moves on to become a second intermediate. And the transition state, it is between the 2 intermediates. This is the second transition state. Finally, the last step is the second reaction intermediate. Goes to the third transition state, becomes finally more stable product. So that's the difference between the transition state and the intermediates. Intermediates are very stable. They are the low energy state. They are still higher energy than the reactant or product, but they compare with the transition state is much more stable. Transition state are the peak on the curves. There's one in physical organic chemistry, the Hammond Postulate. It is a hypothesis. Because this hypothesis has never been thoroughly proven. It is a hypothesis. The hypothesis is if you have a energy diagram and start from the reactant and become product, on the curve, on the reaction energy curve, if 2 points are closer, then their structure must be more similar than the 2 points further away from each other. So this hypothesis is intuitive. And so basically, we imagine those curves. It is the structure gradually change. It's almost like a slow motion for a very fast reaction. And the time points on the curve closer, that means the structure are similar, slowly evolving. And that's the Hammond postulates. There's some, okay, there it is. One of the application is when we have the exothermic or exothermic versus the endergomic or endothermic reactions. The curve, for example, this is an endothermic reaction. The endothermic reaction, it goes through a transition state. Because the nature of this kind of curve, if you draw the curve for endothermic reaction, transition state and the end product is closer in energy. Therefore, according to the Hammond postulates, the structure of the transition state, even though we cannot really see it, we cannot catch the structure, the transition state in the energy diagrams closer to the product than to the reactant. So the transition state must be closer to the structure of the product than the structure with the reactant. Okay, so this is kind of abstract, but because endothermic reaction, the transition state is a high energy state, and it should be closer to the high energy state of the between reactant and product. Endothermic reaction, the product have high energy, and therefore the product structure should more resemble the transition state than the reactant structure compared with transition state. Anyway, we don't have much specific examples in the lecture, so just let's put it down here like this. Exothermic reaction, reactant have high energy, and therefore the transition state must be more similar to the reactant than to the product. That's another argument put forward by the Hammond postulates. So we might be able to see this kind of question in the Zaplan homework. And now we are getting to the actual chemical reactions in organic chemistry. What structures make the reaction happens or not? In organic chemical reactions, electrostatic interaction is very, very important, which means the attraction between the opposite charges is very important in affecting how does an organic chemical reaction taking place. And so if two reaction site locations have the same charge, that'll make them very difficult to react. If the two reaction locations have an opposite charge, the reaction is relatively easy to take place. And so it depends on the structure. For example, the methyl chloride. In a methyl chloride molecule, the chlorine is more electronegative than the carbon. So the carbon is slightly positive and chlorine is slightly negative. And versus the lithium, methyl lithium, they call it methyl lithium. Methyl lithium, lithium is a low electronegativity metal. So when it forms compound with carbon, the carbon has a negative charge, act like an anion, carbon ion. So in this case, the carbon is a negative charge, and this carbon is more likely to attack some positive charge carbons or whatever ions or structures. So the same carbon, what kind of charge, really depends on what kind of atoms attached to the electron activity difference. And in chemical reactions, in the organic chemistry especially, we have a term for some species, some structures with the formal or partial negative charge on the atom. And such atom, because the partial negative charge, they are more likely to attack the positive charge of another structure. And this kind of a structure, we call them nucleophile, because in the atom, the nucleus is the positive charge. And so, for example, the nucleophile we have, first one, the carbon ion. When you have a lithium combined with a methyl group, the carbon has a negative charge. This carbon negative charge, so is a nucleophile. It'll attack the positive charge of some other atoms or structures in the molecule. And then this is a very strong base, S oxide. S oxide is the SNO, lose proton, becomes anion. This is also very strong nucleophile because full negative charge. SNO, even though the molecule is neutral, but there are lone pairs on the oxygen. And oxygen also, because the low electron activity of the hydrogen or carbon, the oxygen has a partial negative charge. So that makes the oxygen also have a tendency to attract a positive charge in the different structure, being a nucleophile. Okay, lone pairs, any lone pair is a nucleophile. And likewise, the ammonia is very good nucleophile. Amine, they are all good nucleophiles, just randomly through some other examples. Because any kind of amine has lone pairs of nitrogen. That makes it a very good electrophile, nucleophile. And then the sulfide ion, a structure with sulfur, also have negative charge. So that's a very good nucleophile as well, those lone pairs. The alkene can be nucleophile because the pi electrons in the double bond are the high energy electrons. So that very mobile. And since their electrons are high energy and they're negative charge, they can attack some positive structures, positive charge structures. The nucleophile, because they are the lone pair donors, and they are the Lewis base. Okay, the Lewis base is in the acid-base chapter we went over. So that's the first nucleophile. We'll see this in organic chemistry all the time. The counterpart for the nucleophile are the electrophile. Okay, the electrophile. The electrophiles, from the word you can see, they are attracted to electrons or attracted to the negative charge. That means the particles, atoms, carry formal or partial positive charge. Interact, they can attract a pair of electrons, and this we call them the electrophile. So the electrophiles are typically either partially positive charge or full positive charge. And in organic chemistry, for example, the carbon, this carbon, because bonded with high electron activity chlorine, it has a partial positive charge. So this carbon, it is a electrophile. It attracts a negative charge or lone pair. The carbocation. Carbocation, we went over this before. It is a non-octet, 6 valence electrons around this carbon, and it of course attracts electrons or lone pair electrons. and that makes them the electrophiles. So the carbocations, there's some other structure are the electrophiles, are the carbon in the carbonyl group. Carbon in the carbonyl group. This carbon has a slightly partial positive charge, and this oxygen is partial negative. So this carbon, it is electrophilic. Electrophiles, they receive electron pairs, so they are the Lewis acid. So that's nucleophiles with the versus electrophiles. This slide is slightly different from the PowerPoint. I just updated PowerPoint in the, from Canvas. This is a structure that has multiple locations can react. And if I ask you what are the nucleophilic versus electrophilic sites, so the nucleophilic sites, they are typically have lone pairs or has a negative charge. Lone pairs, negative charge. Electrophiles, they are the either has a formal one positive charge, or because the polar bond make the carbon positive charge, partial positive charge. So if it goes through this fairly quickly, these are the atoms or the arrows point to the site we're discussing. This oxygen, there should be, since they're lone pairs, so that make them nucleophilic because it has lone pairs around. And also because the carbon and hydrogen make this oxygen slightly negative charge. And this is the carbonyl. The carbonyl oxygen is lone pair, so the oxygen is nucleophilic. This carbon, because the electron being pulled away by the oxygen, it attract, it is positive charge, attract negative charge electrons. So this is the electrophilic. And this nitrogen has lone pairs, one lone pair. With this bonding with the carbon, hydrogen, this nitrogen also has a partial negative charge. So that's the nucleophilic. This carbonyl has a positive charge. And so this carbon, it will have a partial positive charge. So this is the electrophilic. Another way to put this structure, the resonance, if we draw a resonance, this structure, it becomes, by move this arrow to the oxygen, we have resonance like this, which will end up, the carbon has a positive charge, so that makes it electrophilic. The resonance is part of the game. In our class, we just need to focus, recognize give you structure based on the electron activity or formal charge in the structure. You decide electrophilic or nucleophilic. In the next chapter, we'll focus more on the actual reactions. Okay, so next, this is double bond. Double bond has pi electron, which is a high energy, very similar to a lone pair, so that makes them nucleophilic. So this is nucleophilic. Finally, last, this is the alcohol lose proton, has 3 lone pairs. So that's a highly electrophilic, a highly nucleophilic. Electrophilics are the positive charge, attract to electrons. Nucleophilics attract to the positive charge nucleus. That's electrophilic versus nucleophilic. The arrow pushing is the end of this chapter 6. We went over the acid-base arrow pushing, where the lone pair come from the base, attack the hydrogen, and break the hydrogen with old acid bond, form a new structure. but we have more. So today, we'll go over these 3 kinds. There's 3 more kinds of arrow pushing. And also in the future, we'll see them one by one. In the coming chapter, we'll see 2 of them. With 2 of them. Maybe this coming chapter we'll see the number 4 also. So today we'll go over each one of them, and we're supposed to draw them, give you a test, give you a practice exam. You should be able to draw those kind of arrows in each kind of reactions. The arrows basically start from the lone pairs, start from electron pairs, and it will form bond. And this electron pair can be the single bond, or can be from the double bond, or can be from the lone pair. So all the different possibilities. The electron proton transfer is the one we studied in the acid-base chapter. So here, just I draw those arrows. And so once you get back home, when you review this PowerPoint, you should practice drawing the arrow just like I did before. So for exercise, we'll show you the reactant and product. But students supposed to use arrows, proper arrows, as you practice in the Zeppelin homework. So for example, here we have a ketone, and the product, the ketone attached one more hydrogen. This hydrogen must come from this hydronium ion. So the arrow pushing, you start from the arrow here. Attack the hydrogen. So this hydrogen, remember hydrogen only needs 2 electrons to become stable. Now there's 2 electrons already coming. So the hydrogen to become stable need to break this bond. And to break the bond, the bonding electron between hydrogen and oxygen will become on the oxygen. So after this arrow pushing, we have this product, and this hydronium becomes start with this lone pair. Now you have the bonding electrons land on the oxygen. So this oxygen, now you have 2 lone pairs. So the other product is water. Normally we don't show the water as the other product. We show the main organic structure. So that's the process. It is a protonation of a ketone. So that's a protonation. It can be also for deprotonation. So this is the example we have. This is a amine. Okay, you have nitrogen with 2 hydrogens and with a methyl group. So this reaction we have, you can see from here becomes this anion. It lost 1 hydrogen. So this reaction, again, start from the base. Okay, this is the amines be deprotonated. So the reactant, the other reactant must be the base. The amine now acts like acid. So this arrow attack the hydrogen, and the hydrogen, this bond need to break to keep only 2 electrons on the hydrogen, become stable. So after this, the amine becomes a amide ion. And the other product is the methyl anion, it's carbon ion, gain a proton, become the methane. So this is the other product. Oftentimes it causes byproduct. So deprotonation is very similar. The only difference is the base can attack. The base use lone pair electron to attack the proton, hydrogen. And you have this is the last one. The last one, well, the arrows are showing you. So here is normally there should be some kind of base. Okay, normally it's maybe a very, very weak base. The base is an attack, and then you break this bond, becomes a ketone. So that's the proton transfers. And we have seen this before in the acid-base chapter, which was in our test. And there can be multiple arrows. So these are, this is a ketone. We have a hydrogen here. And you can see the final product. The question we give you in the practice will be similar to this. We'll give you the reactant, give you the product. You need to use arrows show what happened. And so compare with the beginning, the left hand, the reactant, with product. There's a fairly significant bond change. You can see there's a single bond here in the beginning, single bond. Now becomes double bond. So the arrow pushing, there should be a bond forming change. But still, this carbon will have two more hydrogen here. Those two hydrogen will stay in the final structure. Only this hydrogen being removed. And so this is typical deprotonation arrow pushing. Start from the base, start from the lone pair. Okay, this bond will break. This bond break, we can either land on the carbon, or better yet, land on the single bond. That way, there'll be new bond formed. So remember, the arrows more meaning electrons. When the electron going somewhere, that'll either add a lone pair or add one more bond, or add one more, at the same time add one more negative charge. And here, this arrow landing on the bond, that'll make the double bond. And also, if you look at the final, we have an oxygen negative charge. To make it one step, we just make it an arrow start from the pi bond, get to the oxygen. So you have a one step, 3 arrows. The other way to write this, which is okay if you write like this, I guess there's nothing quite wrong. You write like this first. You form a carbon ion with lone pair first. And then the next step will be the resonance. Give you the final product. Write one step is the most common. So this is, you can see there are multiple arrows in proton transfer. The reason just because there are so many changes in the structure. If you include in one step, there's a, you can see this bond. You can highlight all the bonded changes. Let's see. Okay, you can highlight all the bonded changes. So this is bond changes. This bond changes. This bond broke. So multiple changes use multiple arrows for each change. And so that's, yeah, that's what the next part. It can be viewed as 2 steps, or you can do the 1 step just shown here. The following diagrams basically show the alternative. Alternative is views 2 steps. Those arrow pushing steps, keep in mind it is a hypothesis. It is how the organic chemists explain how does a reaction taking place. And most steps are never been observed. The arrow pushing is never been directly observed in the chemical reaction, but just in to rationalize, to explain what happened, we use, and it makes sense because electrons are very small and the negative charge move very fast, so they can easily shift around to form new bond and break the old bond. The second one is nucleophilic attack. This is a new kind of arrow pushing. The nucleophilic attack is come from the nucleophile. Okay, it comes from the nucleophile or nucleophilic site. electrons come from nucleophile or nucleophilic site, which is rich in lone pairs or pi electrons. And the attack happens on the electrophilic site, which is a positive charge. So, for example, this is a bromide ion. Bromide ion has 4 lone pairs and 1 negative charge. So that's perfect for electrophilic, the nucleophilic stuff. It is attracted to the positive charge. And carbocation, it is a form of positive charge, so it attracts electrons. Then the arrow pushing reaction, it is this whole bromide, use a lone pair, form a bond on the carbon, on the carbocation. It is one step. And after this step, between bromine and carbon, the new bond is formed. The new bond is formed. So that's the electrophilic attack. It looks very similar. The only difference is no hydrogens involved in such a process. In the acid-base chapter, proton transfer is the base use lone pair attack a proton, and the proton has to break the old bond. But in the nucleophilic site, nucleophilic attack, it is just the positive charge, negative charge, electrophile, which is nucleophile. The nucleophile is negative charge, attract to the positive charge electrophile, and form the one reaction. So the arrows, it form an atom and attract to the positive charge. So the lone pair electrons end up being shared and form bond. Electrophilic attack, it form new bond between the positive charge and negative charge. So it might have 2 arrows. This is a reaction you will see in the next semester. And so basically, when we use arrows, we need to compare what happened between the reactant and product. The product here and reactant. So if you write down the one step, so let's take a look at what happened. What bond changes? The bond changes, you can see there's bond change. There's bond change. And also there's a bond change. This is a new bond, not in the reactant. So this bond, it must be between the reactant and product. We form this bond. So there's 2 bonds getting involved. And to use arrow, okay, so I need to erase all this stuff. Interesting. Okay, I see what was that. Okay, so first realize what happened to the bond, and then we decide to use the arrows to draw those. And you can see the this oxygen, it formed bond with carbon. So this is how you start first. This lone pair. And the reason why I attack here, because this carbon is bound with 2 electronegative atoms, chlorine and oxygen. So this is a highly, very strongly positive charge. It attracts lone pairs. So that would be the first step. But once the first step formed, it is very similar to resonance. And you can see this carbon now you have 5 bonds. This is not possible. So we need to have a next step. they are moving away. And also, if you compare with the look at the final structure, oxygen has negative charge and more lone pairs. So this pi electron must be moved away towards the oxygen. And so you can see this is basically a double arrow reaction. And it's in some ways reminds us of the resonance. But the difference is resonance is within the same species, same ions, same molecules. Whereas nucleophilic attack is happening between the two species. The nucleophile with negative charge lone pairs form bond with other structure. And so that's very similar to the resonance. Any questions? We got quite a few arrows to push around, but start from the lone pair or pi electrons, because those are the nucleophiles. The number 3, the third kind of arrow pushing, is a loss of a leaving group. Loss of a leaving group. It is part of structure because bond breaking, it changes. It's been lost from the main structure. And this has actually really happened. It's a third butyl bromide ion. And it can become a carbocation and bromide. So for this process, if you draw the arrow, we draw the arrow. And you can see look at the final, we need to have a single bromide, a free bromide ion. So this pair of electrons start being shared, now completely goes to the bromide. So when this arrow happens, since the arrow leaving the single bond, the single bond breaks. Single bond means there are 2 electrons. And now the 2 electrons completely left, no longer shared from the carbon. It goes to bromide, bromine, becomes bromide. And this carbon starts, because it has a 1 electron in the share, now loses 1 electron, completely lost 1 electron. It has a positive charge. So basically, whenever arrow leaving somewhere has a positive charge, and arrow landing somewhere and have the charge become more negative. And that's just like in the resonance. So pretty much very resemble the resonance reactions. And so this is a little practice on shows you all the arrows and let you predict what happens. And when you have this kind of exercise, it's kind of fun to do. Keep in mind, most structures should maintain bonding, maybe changes from single to double or double to single, but the linkage is still the same. There's only minor changes in the structure. So I pretty much just copy the structure, but I'm ready to change some of the bond because there are some arrows moving back and forth. There are some arrows. So I maintain all the main structures. And you notice this oxygen, the lone pair start from this oxygen with negative charge. And this lone pair land on the single bond. So that means the single bonds are two electrons. You add one more pair of electron, becomes double. And then also the oxygen, since electron leaving the oxygen negative charge, the oxygen becomes less negative, one less negative charge, or one more positive charge, become neutral. So after arrow moving, this oxygen become neutral. And you look the double bond, now the arrow moving out of the double bond. That means out of 4 electrons, the double bond electrons, now I have only 1 pair left. Okay, so the double now becomes single bond. And this arrow land on the single bond. That means the single become double. It's kind of just like a resonance we did it before. Okay, and this double becomes single. Double becomes single. We keep a single bond. And this double bond arrow move to the, so this bond become double. And finally, this carbon is supposed to bond with chlorine, but with this bond, with this arrow, that means this bond no longer there. You lose one bond. This carbon will lose one bond. With OH, it's no change. The other product is chlorine with 3 lone pairs, and the arrow join in, so you have 1 more lone pair. This is a chloride ion. So that's the, with 4 arrows interchange in one step. They call it concerted change. Concerted arrow pushing. You basically have a 4 arrow movement. It happens all at once. So the final, you have this carbon lose a chloride ion. Next semester, you will learn organic chemistry, see a reaction like this. More arrow pushing here. We have several steps. This is exercise normally we'll do as a demo. The key is to watch what happened. Are there any new bond form? Are there any bond changes? Any charge changes? The arrow pushing almost always end up as have charge change, and always have bond change. So the first reactant, this is, let's label this as A, B, C, and D. These are the 4 the main structures we are to discuss. So you can see the first step from A to B, that's a new bond being formed. Form new bond, it can be just simple as, and notice this, it is come from the other reactant, hydroxide ion. So the reaction is simply just start from the nucleophile hydroxide, attack this carbon. This carbon is electrophile because the electron is because positive charge. And you notice there's also this bond change. This bond changes. So the double move away becomes single. And that's how the first structure is formed. Okay. So that's the first arrow. We have a lots of analysis, but kind of make that messy. Okay, so what happened to the second step? From here becomes this. From B becomes C. From B becomes C, there's a major change. You have to really be very careful. What bond changes from B to C? Is this bond change or this bond change? Which bond changed? You can see this piece, a oxygen negative ion with methyl group, with acid group. That part broke. So it is actually this bond breaks. This bond breaks. And also notice this oxygen negative charge becomes an oxygen carbon double bond. So there are 3 lone pairs. One lone pair need to move away. First step, it must be the start from lone pair, PP double bond. And then the next step, because this bond need to break, we make it a break by arrows moving away from the single bond. And arrow land on the oxygen, so the oxygen in the end have negative charge. Second step, the arrow pushings are such. And that's how we get this product. Okay, finally, there's a from C to D change. From C to D, change is taking place when you see this oxygen attract hydrogen, where this oxygen lose hydrogen. This is typical proton transfer. And this is a base, so base attack the hydrogen, form bond with the hydrogen. And this bond need to break, so the oxygen end up has one negative charge. This is the last step from C to D, the arrows. The C to D arrows, it is the just proton transfer, just like we studied before. So these are the 3 steps, organic chemical reaction, and their arrows pushing back and forth. Each step have 2 arrows. The 2 arrow synchronized or concerted, it reminds us of the proton transfer. The proton transfer from the base to attack, and then old proton bond breaks. 2 arrows happen at the same time. So. Any questions on the arrow pushing in those steps? When you do the homework, when you do the quiz, you're supposed to show your arrows moving more or less like this. This is a more than a 3-step reaction. 1, 2, 3 step reaction. So there are 3 arrow pushings. And arrow pushing again takes some practice. Definitely homework on the chapter 6, chapter 7. There's a fair amount of arrow pushings.
I have a question.
Yes.
So for the one that you labeled B, how come that?
Okay, the carbocations, we saw the leaving group, the terbutyl bromide, and break the bond, form a carbocation. The carbocation, in this chapter, we need to know the carbocation, it is carbon has a positive charge and a non-octet have only 3 electron groups, 3 electron groups, 6 electrons around. The carbocations by nature are not stable. But there's some structures that make it more stable than the others. That is when the carbocation has alkyl groups, and especially the any alkyl groups around. That'll make the carbocation more stabilized. Any alkyl group, such as the methyl group. The methyl group have a 3 CH bond, and those 3 CH bond, we call the hyperconjugation. Hyperconjugation. It is basically when the carbon hydrogen bond, there are 3 of them. This bond, it can stabilize as if it is the pair of electrons, sort of kind of shared into the empty p orbitals in the carbocation. And this we call a hyperconjugation. It makes them more stabilized. And so that's the, we call it hyperconjugation. Basically, any alkyl groups has a possibility to make the carbocation more stable. And so because the methyl group, it can go through the hyperconjugation, that means as the carbocation structure changes with more and more alkyl groups around to replace those hydrogen, it can become more stable. The methyl carbocation is the least stable because there's no methyl groups around, no methyl groups, CH3, or any alkyl groups. But when you have the 1 alkyl group, so now you have only 2 hydrogens around. This we call a primary because this carbon has only one more carbon linked. This carbocation become more stable because this Alkyl group here can give hyperconjugation, making it more stable than the single methyl carbocation. As you replace more of the hydrogen with the alkyl group, become more stable. A carbocation with two alkyl groups is more stable than the carbocation with a single alkyl group. And it getting even better when all the hydrogen on the methyl carbocation replaced by the alkyl group. That's the most stable. Tertiary, which means the carbon linked with three alkyl groups, that is more stable than all the others. More stable than the others. And the carbocation stability difference, it can cause something interesting in the organic chemical reactions. We call them rearrangement. The rearrangement is one of my favorite reactions in organic chemistry. Rearrangement is the alkyl group, sometimes a hydrogen, shift location from one carbon shift to another. And oftentimes, this is because the carbocation stability preference. Yeah, so the this is carbon rearrangement is intramolecular. It happens within the species itself without any attacking species, any electrophiles or nucleophiles around. It happens in the molecule. Because it happens within the molecule, it can happen very quick. It's very fast. Rearrangement reaction typically is very fast. Okay. And so the carbocations, there are two kinds of them. This is the first example when you have, this is a secondary carbocation, secondary, use 2 degrees, secondary carbocation. The rearrangement comes from the hydrogen. The hydrogen, it takes 2 electrons with it together, change location to here. Since hydrogen with 2 electrons move away, and that we call hydride, because hydride means the hydrogen negative charge, which means the hydrogen have two electron pairs. The two electrons, hydride ion, is hydride shift. This hydride shift, this whole entire hydrogen move away, and they will relocate to this carbon. And because this carbon loses the hydrogen negative, it becomes a carbocation. So the arrow pushing. Okay, the arrow pushing is one step. It looks very simple, by the way. It looks very simple. This means this bond will break, and the hydrogen with a lone pair move to a new location. And after moving to a new location, you notice this carbocation now has 3 alkyl groups, 3 methyl groups. This carbocation is tertiary carbocation, much more stable than the secondary. So that's the driving force for this reaction taking. See any carbon-carbon bond change. You won't see the carbon-carbon bond change. The next one, methyl shift, this seemingly more common, and it can be very interesting because the whole backbone, the molecule changes structure. So this is an example. When you have this carbon atom is quaternary because it's bound with 4 carbons around. It's kind of crowded. But anyway, when you have a secondary carbocation around, this whole entire methyl group with electrons shifted away. And after this shipment, rearrangement movement, this carbon has the methyl group. And this quaternary carbon lose one methyl group, lose not only methyl group, but also the pair of electrons sharing between. So this carbon becomes a tertiary carbocation, become more stable. So either case, either hydride shift or methyl shift, the final end carbocation is more stable. And the methyl shift is more interesting. You can see the bonding complete change. We started with quaternary carbon. Now that is completely gone. You have only the tertiary carbon here. So those rearrangement, the arrow movement is very simple. Just one arrow moves. The arrow from a single bond, so that a single bond will break. And the arrow move to a new location, the whole methyl group or hydrogen relocate to a new location. So take some practice on the sampling homework. We're going to be more familiar with all these movements. This is a little practice on all the arrows we'll have. It's actually the actual reaction in the next chapter. And maybe the following chapter, we have those reactions. But here, I just, together we practice on how to use arrows. So basically start from the first structure, every step, watch out what changes. And as a summary, we learn about those 4 different arrow movement. Proton transfer is one we studied before. It is arrow toward the hydrogen, and hydrogen bound move. That's the proton transfer. Nucleophilic attack, it is something lone pair. Okay, lone pair attack to some partial positive charge. That's a nucleophilic attack. Nucleophilic attack, typically only one arrow. And next one, loss of leaving group. Leaving group is when the carbon was bound something and this entire group left. Entire group left, it'll cause the carbon has positive charge. And finally, rearrangement. Rearrangement is some structure. It is nearby has a carbocation, completely moved. That's the simplified version of those 4 arrow movement. And this reaction, it happens in the following chapters. We just need to kind of practice how we add those arrows. Okay. So start from the first reactant. Watch what happened with this. You can see there's only one part of structure changes, only the oxygen. Oxygen gained 1 more hydrogen, gained 1 more charge. So this must act like a base. Act like a base, gain proton. It's a proton transfer. So the arrows is a base, so use a lone pair to attack the hydrogen. And this hydrogen can only maintain single bond, so this bond need to break. So that's the first step, arrow pushing, is the proton transfer. Okay, if you write down what kind of attack, it is a proton transfer reaction. A proton transfer reaction. Okay, second step, we have this structure and lose water becomes this. The losing water And you can see the end structure, it does lose the water H2O fraction. And the arrow pushing, it should be, this bond need to break. So bond break. And then notice the water, this part have, oxygen has a positive charge. Water have no positive charge. And also notice the final, this carbon has positive charge. So that means this bond breaks, electron should go with water. Electron goes with water. And once it draws this arrow, this bond is become missing, it's gone. And the carbon, because lost, carbon will lose the pair of electrons in between. And basically lose one electron, become positive charge. And the water, this section has a positive charge, but once a lone pair landed on the oxygen, it becomes neutral, it becomes just water. So the single arrow, this is a leaving group. This is actually the loss of leaving group, type C in the arrow pushing. And next step, we have a carbocation, and then, oh, interesting. We notice the line structure change. This carbon, it end up has one more carbon here. And this carbon lost one more carbon. That's a carbon shifted. It is rearrangement. And rearrangement is simple. This bond need to break. And the methyl group here carry both electrons and land on this carbon. It should give us a new structure, new bond. This bond breaks. And also this carbon, since lose the two electrons in between, the carbon has positive charge. So what kind of changes for this reaction? From this to this, what do we call this kind of change? We have proton transfer, nucleophilic attack, loss of leaving group, rearrangement. Which one? What kind of change between these two? Nucleophilic attack is a formal bond. Leaving group, loss of leaving group is break a bond. But this is you have a bond forming, bond of loss at the same time. And it's not proton transfer. There's no proton move around. This is rearrangement. Type D, the rearrangement in a bond. And finally, we'll get to last step. The last step from the carbocation becomes a bromide. It reacts with bromide. It should be a simple reaction because we need to form a new bond. And bromine now become part of the structure. So the bromine should use the bond. It's a one step. Just form a bond. And the bromine, because it uses a lone pair, no longer has negative charge. And this carbon gain the pair of electrons from the bromine and become neutral. And so this is this one step. It is a nucleophilic attack. Type B in the reaction. The arrow pushings we learn in the acid base, but now we can see there's more kinds of arrow pushing. This is pretty much all the organic chemical reaction the arrow pushing will be, just 4 kinds. And David Klein's book, it basically summarizes these 4 arrow pushings and put into a half of a chapter to explain. But this takes some practice, and Zeppelin really helps in the arrow pushings. The arrow pushing in organic chemistry is very important. How important? Okay, start from next exam and the second midterm and final. Each exam, I would say about 20% of the points come from the writing the reaction steps, the mechanisms, which is basically the arrow pushing. So start from the second exam all the way to the final. So keep in mind that will be higher weight of the questions. It comes from the arrow pushing. How does reactant interact, form bond, and break the bond? There will be numerous bond pushings for each chapter. So this is pretty much the end of the new material. We'll go through some of the extras. And these are all just, I draw those steps. You can have more than combining arrow pushing patterns, like the 4 arrow pushing patterns. The 4 arrow pushing patterns are the proton transfer, nucleophilic attack. This is form bound. Okay, this is a form bound. This form bound for B, nucleophilic attack. Proton transfer, both form and break same time. Both form and break. Loss of leading group is break the bond. Okay, loss of leading group is break the bond. Rearrange, it both has a break and form. So with the 4 arrow pushing pattern, is very important. You make a table, compare and contrast. What is the similarity between these 4? What is the difference between these? And so this is the reaction I'm supposed to use arrows to show. So watch what happened. You can see the chlorine somehow break. So this bond need to break. Okay, so you have a free chloride ion. And in the new structure, we can see this bond formed. This bond is new. So that means the hydroxide need to form bond with this carbon, and this carbon need to break bond with chlorine. To form bond, use a nucleophilic attack, okay, because that's what a form bond. Step B. Attacking on the carbon, because you are to form bond with the carbon. Which form bond with carbon gives the alcohol. And this bond need to break because the carbon need to maintain octet. You cannot just form bond without breaking. So break the other bond. It'll give us form the chloride ion. So that's the. It is 2 steps happen at the same time. This reaction is typical in the next chapter. We call it the nucleophilic substitution. Substitution, because you have the forming a new bond at the same time, break the old bond. So the old bond being substituted by the new groups. General arrow pushing rules. These rules typically start from the arrow. Where start from? Start from a lone pair, and typically have negative charge. Very often have negative charge. Sometimes don't, but with lone pairs as a Lewis space, that's where the electrons bond start from. And so, for example, this is a nucleophilic reaction. You form a bond. This is a nucleophilic attack. Nuclear attack. And this bond breaking, it is it's loss in leaving group. This is a leaving group, okay, because it breaks in leaving group. It has 2 steps together. What's wrong with this arrow pushing? The start place, there's no long pairs. As a Lewis structure, as the arrow pushing is not good. You need to have a long pairs. Should have long pairs, and the arrow should start from a long pair. Okay. Do the attack land on the carbon? This is good. This is good. But you can see the arrow. You start from the carbon. This is not right. The arrow has to start from the pair electrons, either bonding pair, like the single bond. Instead, this is better. Okay, so the arrow should not start from atom. You start from a lone pair. So the main problem is you should start from a lone pair. And Oh, one more problem with this one. It's actually my problem, sorry. The arrow should land on the chlorine atom. Arrow should land on the chlorine atom. Okay, so that's my problem. Start from lone pair. And the chlorine should have multiple lone pair already. Okay, so that's the main problem with this. The end, okay, the arrowhead, or the fish hook, whatever, it end on a nucleus means an atom. End should end on a nucleus or between two nuclei, which means start from a single bond become double bond. Okay, become bond. Arrow should end on nucleus. Start from lone pair, but has to end on the where the electrons be needed. Okay. So this this arrow landed on the carbon. You can see land on the carbon. And this arrow also land on the chlorine. Number 3 is, and also try to maintain octet. That's very important. This is a single arrow. The problem is once the lone pair land on the carbon on the nucleus, this carbon now you have 10 valence electrons around. That will not be octet. So to maintain octet, this bond need to break. This bond need to break. Among the organic chemical reactions, we almost never break the octet rule, because we know even though like phosphor, sulfur can be non-octet, but those atoms are rarely involved in the organic chemical reaction at our level. So we don't allow the non-octet, except hydrogen. And so that's, so we have these reactions. So we have the four key patterns: the proton transfer, nucleophilic attack, leaving group, and rearrange. Those four are the one that happens in organic chemical reaction. The others, if it doesn't belong, then you have those don't have this kind of reaction. And so for example, this is the someone draws this kind of arrow. What is the problem? Okay, first of all, the arrow start from lone pair. This is allowed. Okay, start from lone pairs is okay. But this arrow landed on this carbon. This carbon, keep in mind, there are 2 hydrogens already, and there's a 1 methyl. After joining in the lone pair, this carbon now you have 10 valence electrons. It divided octet rule, so that's why it's not allowed. This is possible only if some leaving group break the bond, take the electrons away. Then that can happen, but it has to be a good leaving group. So there's more practice on the arrows. We have only about 2 minutes. Let's just kind of practice on this. This is also a typical reaction in organic chemical reaction in the next semester. And so basically watch between every step you have a reactant. This is the intermediate. The first intermediate, so intermediate number 1. And so this another intermediate. 2. We have 1, 2. Yeah, we have a 3-step reaction, 2 reaction intermediates. And so every step you watch what happened. So between this and this, you can see there's a bond change. This bond is new, so there's a new bond being formed. New bond formed is a nucleophilic attack. And also you can see the double bond becomes single, and oxygen gain negative charge. That's where the electron leaving and join the oxygen. So that's the first arrow moment to give you the first reaction intermediate. And now you look, this reaction intermediate 1 becomes reaction intermediate 2. So again, watch what happened. And notice from intermediate 1 becomes intermediate 2, this bond is new, it's being formed. And also this bond is missing. Wait a minute, which bond? This bond, okay. This entire structure has been lost, been cut away from the structure. So this bond need to break. This bond need to break. And this single bond need to become double bond. Single become double is very common use a lone pair to just one lone pairs. It's almost like a resonance, this step. And next step, we're gonna break this bond. Because in the end, you can see the S-oxide as free part. This piece completely need to be lost. So leaving the single bond, join the oxygen so that we break this bond. Oxygen gain negative charge. So that's how from intermediate 1 become intermediate 2. Okay, finally, we have an intermediate 2 become final product. Let's see what happened. Okay, so you can see this hydrogen somehow has been lost, and this oxygen gain negative charge. This is typical deprotonation. We lose hydrogen and gain negative charge. And also the S-oxide becomes alcohol. And so that's the, it should be the typical proton transfer. So that'll be the second step, which leads to the final product. The first step, nucleophilic attack. And this is just loss of a leaving group. You leave the leaving group, you lost leaving group. And also there's one part is the forming of bond within the structures. And the last step is just a proton transfer. Proton transfer reaction. So there's a lot we can practice on the structures. There's more arrow pushing. So those of you interested, I'll give you extra credit. So those of you show me all the arrows. It can be an extra credit practice. But we have ended the